Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To astrophysics simulations, and today he's going to be talking about simulations to help understand the supermassive black hole at the center of the Milky Way using the 30,000 core SciNet cluster. So welcome, Willy.
Okay, so I'm mostly talking about actually work done by my PhD student, Bija, who just defended his thesis on this topic after working away at this for 4 years. So this is 4 years worth of a PhD thesis that I'll be explaining some of the work and the background, the summary. So the astrophysics, especially black holes, have the intrinsic challenge of making it difficult to do controlled experiments. So if in particular it's hard to make your own black hole, hard to control what goes in and what comes out. So there's been a lot of debate of what happens near black holes, how things really go in and how they form and how they evolve. And in the absence of controlled experiments, you never quite know how you test any of these hypotheses. So there have been various groups, including us, setting up numerical laboratories where you can make a black hole on a computer. That's the second best thing to actually making one in your lab. So now we can actually set things up and control environments, control the physics, control the initial conditions, and actually see how black holes form and evolve with time. And one of the enabling developments over the past 50 years, I suppose, has been the existence of larger and larger computers. And the ones that we've been using for our work has been the SciNet cluster at the University of Toronto. That's a 30,000 core computer cluster. And we've also describing a bit about our development towards future architectures, which is centered around GPUs, which has the potential for even larger and more detailed simulations. And the scientific part of this work has recently been posted on the archive. In our field, everything gets posted as a preprint electronically before things get published in journals, so this is still undergoing peer review. And this was published last November. Here's a picture of the galactic center. The position of the galactic center is called Sagittarius A star. Sagittarius is a familiar constellation on the sky. This image is probably not as familiar. It's an X-ray image of the galactic center. And at the very center of the X-ray image is a faint point source, and it is believed to be a massive 4 million solar mass black hole that has both stars orbiting around it and also has gas flowing into it. So the X-ray emission we see comes from diffuse gas in the interstellar medium. This is gas that, part of it is mostly gas that either was reprocessed from stars by stellar winds. That's great. Thank you. You read my mind. That's either ejected from stars or stellar winds, or it flows in from the outside. And the stars in the vicinity of the galactic center happens to be at a temperature of around 10 million degrees. And this hot gas, at these temperatures, the primary band in which you can observe the gas is X-rays. So we know the temperature and the density of the gas in the galactic center vicinity. We know how many stars there are. So we know this environment fairly well. The galactic center black hole is, in fact, the probably best understood black hole observationally. It is not the most massive black hole in the universe, black holes that are 1,000 times more massive, but it's not even the closest black hole. There are black holes closer than that in our galaxy, but it is the black hole with the largest angular extent. So it's the the horizon of this black hole is about 10 microarc seconds, which is tiny, but it is still the largest apparent angular size of any black hole that is known to us. So it's the easiest one to study. And also the only black hole for which we can actually image the environment visually, or at least in the X-rays, and where we know the conditions of material around it, so we can actually do a quantitative study. In many other situations, if you don't know anything about it, it's hard to quantify what's going on or not. Must be a way of switching slides. There we go. Now, in gravity, gravity is an attractive force, and it's a 1 over r squared force. And if you put a gas inside of in the vicinity of a black hole, there is a characteristic radius called the boundary radius, given by gm over the speed of sound squared, inside of which the force of gravity is larger than any thermal pressures a gas may have. Meaning that any gas, and we can actually, the image that you saw, can actually image the gas at a resolution of about an arc second, which is about 0.01 parsecs as a galactic center, at these radii you can actually see the temperature and density of the gas. And you know that in that central radius, the gas should just flow in rapidly, because the thermal pressure certainly cannot stop this process. And black holes being forces of infinite gravity, you would think, one would expect that matter should be falling in. And the normal thought has been that if matter falls into a black hole, the gravitational energy that you gain, so as it falls in and flows faster and faster, the basic expectation in the past has been that if it falls in slowly, it has to break and lose its energy thermally. So it's just like if a meteorite hits the Earth, it'll burn up by converting its gravitational and kinetic energy into heat, and it emits brightly. And you can calculate. Since we know how much gas there is, we know how fast it's flowing in, we know the potential depth of the black hole, so we can calculate exactly how much radiation should come out. Now you go and measure it, and you actually find that in fact, the total luminosity of the black hole, it's accreting about a millionth of a solar mass a year. That sounds like a small number, but it's been around for billions of years, so it would have swallowed many, many times the mass of the star. It should actually be about 100,000 times brighter than it actually is observed to be. And that goes in the wrong direction. So in observations, obviously if you expect it to be faint and you observe it to be bright, that may be a problem in your measurement. You never quite know what you've measured. But if you expect it to be bright and don't see it, that's a harder thing to avoid. But you expect to see this brilliant source when in fact you see an object which is only about as bright as our sun, when it should be much, much brighter. So this is not a small discrepancy. This is a very, very large discrepancy. And people have been debating about what causes this. So there are a couple of ways out. Maybe the inference that material is going in is incorrect, so maybe the material is not going in. Maybe the force of maybe something wrong with the force of gravity, maybe something wrong with the force of gases, with the pressure that we think gases should have. Or maybe it is going in, but magically not emitting any radiation. And again, that is has been thought to not be possible, since one can calculate the rate at which electrons collide with each other and emit photons. So this has been one of the enigmatic problems in astrophysics that don't have a generally accepted solution. Now, I should make the caveat that the regime in which you can calculate, the force of gravity, is in the model of spherical symmetry. So if you have a uniform density of gas and have a spherical black hole, that's when you actually calculate these rates. The real process might not be spherically symmetric. In fact, most things are not spherically symmetric. So maybe it's something about the three-dimensionality. Maybe there are other effects that cannot be easily modeled or understood by a simple picture that we have. So I thought I had one more slide before there. Don't. So let me show you the simulation. Here we go. So here we have I'm just going to start the simulation, explain what we're looking at. So here's a three-dimensional simulation of gas falling onto the black hole. Our setup is we have a fairly uniform bath of gas, which is represents the X-ray gas that we saw from the X-ray image at about 10 million Kelvin. So we know the density in gas in the surrounding area. This circle here is starts at the boundary radius. So that's the radius at which the black hole's force of gravity will win over the pressure of the gas. And the color coding of the gas over here is given by the specific entropy of the gas. Now, entropy is one often not quite intuitive property of a gas. It's in an adiabatic process is conserved. So for example, in our atmosphere in the troposphere from the sea level to about 40,000 feet is isentropic, meaning it's a constant entropy. Now the density changes a lot. By the time you get out up to 40,000 feet, there's not much atmosphere left and the temperature goes down a lot. But the entropy but the density and temperature change in such a way that entropy is conserved. And what it means is that as the wind blows and the air mixes, the work done by the air expanding when it goes up is it perfectly balances the change of temperature on its way up. So in a slow process, a isentropic process is reversible, meaning that if some air flows down from a mountain, it's gained exactly the same energy as it lost on its way up. It's an isentropic process. And the naive expectation of gas flowing into a black hole, at least not to say expectation, I guess there's no way to make this repeat automatically. Maybe there's, yeah, here we go, there's a button. Okay, let's not make the mouse better, let's not make the Microsoft mouse better for now, but turn on repeat. There we go. And in this particular case, in the normal process, the gas would flow in at constant entropy, and then the constant entropy, the temperature would go up and the density would go up, and as the densities and temperatures go up, the electrons colliding with each other would start emitting radiation, and you would start seeing the flow. So two things we have in here. One is, of course, we have this circle. In the very center, if you squint, you may be able to see a little blob in the center, and that is our numerical black hole. We don't actually have the full dynamic range yet to simulate the actual size of the black hole, which is about 1/100,000th of this radius. So the actual black hole would be unresolved in a single pixel on the screen, and we don't have the computational dynamic range yet to actually simulate black holes as tiny compared to the accretion radius as our real black hole. However, to get started to understand the physical processes, we can scale up. We can put a larger black hole in this gas and just see what it would do.
I'm sorry. What do the two halves represent?
So we have two slices through the whole system. So we have, if you call this the axis X and Y, then this is X and Z. So in a three-dimensional simulation, you have to pick your axis on which to slice it. And again, generally gas, generically if it's turbulent and flowing out of stars that are moving, will generally have random motions. So it will have angular momentum, meaning that gas, one of the issues that is actually very hard to model by hand is to ask, well, maybe rotation changes the name of the game. So some people have thought, well, if it rotates, maybe that changes the story completely. And as you can see in the beginning, and it'll go back again after the next cycle, in the beginning we have gas with a little bit of rotation, and you could see from it actually is rotating, I forgot which way, I think it was clockwise in this plane initially. And as it rotates, there's a rotation axis, and in the rotation plane you have a centrifugal force, which slows down the gas going in. And in fact, you can see, and you'll see it again at the end of this movie, that the gas falls in from the poles and then flows out along the equator because rotational support has less forces the gas out. And along the poles of this rotation axis, the rotation really doesn't matter. And out here you can then see the pancake forming and things flowing out. So the other things you can see is that gas does get heated by it's called gas dynamic shocks. So it actually converts kinetic energy into entropy. And there's one more phenomenon about entropy, is that high entropy gas is buoyant. So gas, when it turns red, it's tempting to call it this temperature. So at a constant potential depth, gravitational potential, I actually thought this thing goes in here and this thing orbits around and initially flows out. But very quickly, as you can see, the gas, as it flows out, again mixes with other gas that's flowing in, and the whole thing just gets mixed up. And this rotational angular momentum actually, after mixing, just dissipates itself. So angular momentum is only important if it actually were conserved along a flow line. But if you have a lot of mixing, then the low angular momentum material mixes with the high angular momentum material, and in our case, it stops mattering nearly as much. So we just said we have the phenomenon that the gas colliding with different streams causes the entropy go up, and you can see that then you get these convective plumes, the same as when you boil water, when the sun shines on a desert, that you heat. But by heating, actually, obviously the hot gas always convects upward, and you may wonder why, as it convects upward, it cools. So why does it keep going up? It's actually the entropy that stays conserved. So if the sun imparts entropy in the gas, and the entropy is conserved on the way up, it'll keep rising. It'll keep rising until it hits the stratosphere. That's why thunderclouds just keep going up. And here you see the same phenomenon, that the gas, as it heats, convects out. And you also notice that as the gas gets beyond this boundary radius, the motion actually slows down. And that's just because outside of this radius, the gravitational force of the black hole isn't as important anymore. It falls off with r squared. So obviously to have convection, to know which way is up, it needs to know about gravity, and if the gravity is getting weaker, there we go, we saw the shocking of the gas again, and the flow of the fluid initial out and mixing, and you saw the formation of a pancake, of a hot pancake. Yes.
How does this time scale correspond to the actual time scale? Like, if we're seeing what would, I mean.
So the ring falling in. So this is a ring of matter that the trajectory a matter shell would have if there was no rotation and no magnetic fields, and this is the normal solution people calculate to get the accretion rate, would be gas uniformly shrinking at this rate. The time scale of infall of one of these rates at the galactic center would be about 100 years. Is the time it takes from this unstable point to actually hit the black hole. Now it turns out it's the outer part that takes the longest time. So whether our black hole is about 1% of this radius, if the black hole is 10 to the minus 5 of that radius, it's still 100 years. That doesn't actually matter. The last few steps don't take any time, even though they may impact how much entropy is generated. So we're talking about time scales of order 100 years that these things operate at. So you could say, if I looked at this X-ray image, if I came back 100 years later, maybe I would see the gas gone, if it actually were to flow in. But 100 years is kind of time scale that is kind of long, for me at least, to wait. So people are hoping to be able to make measurements closer in where the action is faster. And the action gets faster very quickly. As you can see, things are move very rapidly near the black hole, just because the energies are higher, velocities are higher, and the length scales are shorter. So all the action is happening in the middle. And this is the picture we now have of black holes, of black hole formation, of black hole accretion. So what's new about this simulation compared to what was known before we started on this process is that this is the first what we call global simulation. Okay, before, again, with limited computing resources, what people did is they would take only a little region near the black hole, and then they would force feed matter in. Now, when you're force feeding matter in, you never quite know whether. So basically, you have to specify a boundary condition of matter is being shoved into the black hole, and then the question always becomes as well. How do you know that your answer didn't depend on your boundary condition? Because that's something in a simulation you have to specify. I have to specify what happens at the edge of my simulation. Do I make matter go in? In our simulation, we really don't have this problem because we've got a very large volume, and far out from the black hole, the gas doesn't even know about the black hole. The force of gravity is very weak, so you know that you're in a regime where the things you don't know, which is a black hole physics, don't affect your answer. So I can just keep making this box bigger. In fact, this box, actually the gas goes on for a long ways outside. So in fact, it's causally disconnected from the gas. Just the amount of time it takes for the gas here to communicate with the outside is beyond the length of our simulation. So this is the first time anybody has made a simulation in which you could actually say, I have an answer that doesn't depend on my ad hoc specified boundary condition of my simulation. So I can actually say, I have gas there that's just sitting there, not doing anything, and it keeps going. It keeps going for a long ways, such that I don't have to worry about my artificial boundary conditions. And that, I would say, is the biggest progress, and obviously to do this in 3 dimensions. Again, doing it in 1 dimension, this was solved by Bondi in 1952. So and he did it by hand. It's a nasty equation. Even in 1 dimension, it's a nasty equation, and it's a bizarre function. But Bondi, Ham and Bondi in 52 managed to figure it out by hand. And that's been the only solution that you can actually get without a computer, or even with a computer. So the problem is going from one dimension. People have done it in 2 dimensions. But again, you never quite know whether, since the real universe is 3-dimensional, it's not quite clear what you learn from a 2-dimensional simulation. Well, you may learn that 2D is different from 1D, but it doesn't quite tell you what would happen in 3 dimensions. So it's really easy to be able to relate anything you see to our galactic center. It's probably necessary to do something 3-dimensional, and that's why we can now just throw brute force compute power at this problem to understand this process. Now, this is certainly our picture. I do have to give the caveat that there are certain things that we don't have realistic in our simulation. One is, of course, this black hole is not the same size as the actual black hole, and if you make it smaller, you might worry that a black hole as small as the galactic centers might have a different dynamics in its evolution. There are also discussions of whether there might be plasma effects that we're missing, that the ideal gas description might not be a complete description. So that's why I think our simulation results are not yet by any means universally accepted. In fact, I think most of the community is still skeptical about whether this picture really describes what goes on. Let me first state the main result, which is that the gas, in our case, actually just isn't going in as quickly as you thought, because the assumption was that it stays isentropic and just goes in. What we are seeing is that you generate entropy, so gas actually goes out. So the picture that it can only go in, this assumption in spherical symmetry. So in spherical symmetry, this isn't you can't have convection in spherical symmetry. So things are either going out or in, but you can't have both. In 3 dimensions, well, you can see you can have plumes where stuff goes out and other channels where stuff goes in and things can mix. So in 3 dimensions, clearly, it can be the case that both happen and they run into each other and get entangled. So there's it's clearly a complicated process of mixing and convection that you just can't do in 1D. So the 1D picture just isn't describing the system even qualitatively. So here we have a picture where it is this outflow that collides with the inflow, that the whole thing gets stuck, and therefore the accretion rate is very low, and therefore it only needs a little bit of gas at the center to be heating that can clog up the whole flow. That's our conclusion from our simulations, that the black hole just really isn't doing the naive 1-dimensional process.
And that in turn explains the difference in predicted versus observed brightness?
Yes, we claim we actually explain the difference. Well, between predicted and observed, I put a bit of a caveat, is that in our simulation, in fact, the predicted luminosity is even lower than the observed. Now, the problem is when you observe a luminosity, you see, I would say it's really an upper bound, right? You see an image there, you don't actually know whether the black hole or just stars or, So, with other words, you've got a problem if you predict more than you observe. If you predict less, you've got to ask what you're actually observing. There are many things going on. In fact, most people think probably that the emission we're observing comes from mostly transient flares that are phenomena not associated with a gas, but by plasma processes near the surface that we don't have in our simulations. So that's the flux actually that we see is not related to things that we can easily simulate and that aren't really relevant for the global energetics. So yeah, so this is of course in science only a explanation of a fact which was already posed. Then you ask, well, okay, so how do we know that this picture is really what's going on? We need a way of actually testing this now. So in the lab we can control things, except for that there's still things that we can't quite achieve, like the actual size of the black hole and some of the non-ideal properties of the gas. I think I can switch back over here. And so we can explain luminosity, but that's post factum explaining it. And that usually a posteriori explanations are not counted as scientific, as a scientific proof of anything because you already knew the answer. So we have now we now need to make a prediction of how can you test this. And we have now made predictions of something called rotation measure, which is the rate of change of polarization. So what you can measure about the emission in the radio especially is you can measure the polarization angle. And the polarization as it flows through the magnetic field, the polarization angle gets rotated by the electromagnetic waves interacting with the plasma and the magnetic field. So you see an apparent rotation angle, and this rotation angle will depend on how much magnetic field you have along the way. So if things are flowing and changing, this angle will change. The apparent angle will change with time. So here we plot, and the rate, it's called a rotation measure, is the rate at which the angle is changing. So in our simulations, we can measure that. Okay, we can measure that if you observe this black hole and measure the radiation, then this angle will change with time in some predictables. We've drawn different lines of sight along the black hole. These are 6 different lines of sight toward the black hole, along which we can measure this in the black hole. And this time axis in this picture corresponds to about, in human times, this would be about a century going across. Okay, so this is a slowly well, obviously, if you wait a century, you see a lot of structure, but if you wait for, say, 10 years, you would still see that there is time variable structure when you made this observation. You can ask, well, what about other models? If it were just streaming in and they were just random magnetic fields, you can ask how quickly would it be varying in a normal model? And the answer is, in a generic model, these things would vary on a time scale of an hour. Because every hour, basically, as the fluid goes, as the field, because the polarization primarily comes from very close to the black hole surface, where things are falling in very rapidly. So every hour, a different piece of matter is flowing past with a different polarization angle. So normally, you'd expect this to jitter on a very, very short time scale. And in our simulation, because things get clogged up, this time scale gets stretched out to a year or something. This goes over many characteristic times. So now you can ask, well, how about testing this? So I've been persuading colleagues to use the most recent telescope, the Atacama millimeter array, to actually go and measure this polarization. And this is a new array that costs, I think the actual cost by now is close to $2 billion. It's the most expensive telescope on the Earth, on the ground, not counting space telescopes, ever built. It's an array of, ultimately, it will be 66 telescopes of about 12 meters aperture each. It's a radio array built in the Chilean Atacama Desert at a altitude of, I believe it's 5,000 meters, which is about 15,000 feet or so. It's a high desert. The specialty about this array, apart from costing a lot of money, is that it can observe at very high frequencies. In the radio, it can observe at up to about 1 terahertz. And at 1 terahertz, the galactic center is the line of sight is most transparent. From at low frequencies, the interstellar medium scatters radio waves, and at high frequency, the optical dust obscures it. So this happens to be looking at a window where you can actually see right down to the galactic center. So this is ideal for measuring the rotation measures, and we've been trying to persuade them to actually use this telescope to see whether there's time variability. Down here, this is just a plot of the basic thing you saw in the previous movie, but of course movies, when you write a paper, kind of hard to put a movie in a paper, so what we do instead is we take one dimension to be time and one dimension to be spatial axis. And the color coding here is a magnetic field. So we can see different magnetic fields will have different polarization angles. So the color scale basically corresponds to the polarization angle that you would see evolving with time. So this is stretched out. It's really a four-dimensional data object you have, right? You've got a three-dimensional quantity with time, and you've got a slice. So the previous one is two spatial slices with time evolving. Here's a time and a spatial slice with two other spatial dimensions not plotted. So this is the basic setup of how you present this. So looking into the future, and you say, well, can we improve on this? Can we, or what are computers doing these days? As of 2 months ago, the fastest computer is this fellow called Tianhe. It's a computer that China put together. It's I think it's about a 2 petaflop, 2 point petaflop machine. And it's fast, not only because it has a lot of racks, it does have a lot of racks, but it's actually not based on CPUs. The processing power is all based on graphics processing units. Okay, so these guys have been evolving with apparently without any limits, and we've been exploring, developing our algorithms to run on this potentially very powerful infrastructure. And this presents some new challenges going forward of how we can exploit this facility. So just to give a bit of just general history of what CPUs are doing these days. Of course, I've been I guess doing these simulations since Kevin and I have been playing out with computers for the last 30 years really, since we were kids. And if you actually look at the peak speed of computers, they have changed only a little bit, maybe a factor of 10 or so over the last 30 years. So in our days, there used to be a machine called a Cray. And a Cray had a few gigaflops in those days. And nowadays, your laptop has a few gigaflops. So a laptop is a little bit faster than a Cray of those days, but not by much. Maybe 5 times faster than a Cray, of course. And a Cray used to cost $100 million, and the laptop only cost $500. So it's gotten a lot cheaper. But the basic limitation is that the rate at which a transistor switches really hasn't changed that much. They run at gigahertz, and Cray ran at like half a gigahertz or something. So the actual rate at which transistors switch really hasn't fundamentally changed, meaning that. But what has changed is that the cost per transistor has really gone down by factors of millions over the last 30 years. So the progress has been we can have more and more transistors in a smaller and smaller area using less and less power. Crays used to be huge power hogs. Now the evolution of software and algorithms, however, have really been stuck in the Cray days. Okay, the whole concept of how you do things hasn't changed. The mindset has been primarily serial. So nowadays, when you go and buy your random $5 billion transistor latest CPU that you spend $500 on, it may have 5 billion processors, but it actually executes an assembly code invented in the 70s. Okay, it executes some x86 or x88, it's really an 8080 instruction code that's being executed, which was meant for a totally different purpose in a day when transistors were scarce. So what vendors do, because software compatibility is paramount. If you nowadays sell you a laptop which isn't compatible, nobody will buy it. So you have to be always backwards compatible. So almost all transistors, 99% of all transistors, are spent trying to execute ancient code quickly. So you have these really long pipelines. They can be 10 or 20 instructions deep that just keep executing instructions without So if you have dependencies, well, you try to if you have branches, you try to go down both branches. So you try to you've got transistors coming out your ears, so you just you deploy all your infrastructure to try to make your code a little bit faster. Also, people, you have these gigantic caches. By gigantic, you've got many megabytes of cache on a core. So that's hundreds of millions of transistors storing data just in case you use it. Okay, most data going into the cache never gets used again. 99% of that data is never used again. But just in case, because you don't quite know what the programmer wanted. In those days, they didn't have in the 70s. The 8080 didn't have a cache. So you have to pretend. You have to pretend to do things. So everything is now is a factor of 100 times overbuilt just because you have to connect to the past. So recently there's been a category of processors called general purpose graphics processing units, which is now in every computer, I think. I think nowadays you'd be hard pressed finding a computer which doesn't have a GPU in it. And these GPUs nowadays are actually much faster than your CPU. So on almost any computer that you have, chances are that your GPU can deliver 10 times more flops than your CPU, even on a cheap graphics board, and maybe 100 times more than on a high-end graphics board. And what they changed is that the graphics processing units don't pretend to be compatible with your code. So they don't promise to run any code, that's any legacy code. They only run codes written for this graphics processing unit. Okay, so only games, that's what they call GPUs, only graphics applications and games really run fast on them, or at all. In fact, the clock speed of these often are only 300 megahertz or 800 megahertz. These actual clock speeds of them are very modest, but they have thousands of units doing it at once. So they changed the game and they said, well, forget about trying to execute any legacy code. We're going to make the processor that can deliver the ultimate performance. And if you want to use it, you got to figure out how to make your algorithm work on this, on making use of this new architecture. To give you an example of what this translates into potential costs and performance. And I used to have two photos that I couldn't get to paste on here somehow. Anyways, so SciNet, I think SciNet's on another picture on the next slide, is our big computer cluster in Toronto, for which we paid $30 million from IBM. It's got 600 teraflops, so the cost per teraflop is about $50,000. At the same time, Bija I bought him a new game station. I got him an Alienware ATI Radeon 5870. And that costs $2,000, which has 5 teraflops, not as fast as the whole cluster, but per flop, it costs about 1% of the SciNet cluster. Okay, so it's 100 times. But that's kind of what you scale. If you just ask, what fraction of transistors are actually used for arithmetic in both of these, it kind of scales with what you expect. So just if this is not really rocket science or something. It's not like a breakthrough in some concept. Just saying, well, let's get down to earth and ask, what do you want? Do you want a chip that's run your legacy code, or do you want a chip that's just fast and you got to figure out how to do it? So, Bija figured out how to do it and started coding our black hole simulations for these chips. Okay, I'm not going to rewrite everything. And in fact, it turns out there are actually relatively few applications that make it truly useful. So an individual GPU, it's 100 times faster than your CPU. On the other hand, our SciNet cluster has got 30,000 CPUs and still faster than any single GPU, meaning it would be we couldn't do these simulations on a single GPU. They're just too slow. A single GPU. Of course, now you say, well, clearly, what you do is just buy yourself a cluster of GPUs, put 30,000 GPUs, and then you're really in business. And those are cost no more than 30,000 CPUs. So it's clearly a cluster of GPUs that have relevance for scientific computing. But that leads to an extra challenge that already the clusters already put a big paradigm change of how you do simulations. That now you've got to explicitly parallel. Write multiple threads that communicate with each other over MPI. That already was a major headache. Now, in addition to doing that, you've got to figure out on each node how to now send the data into a GPU, how to get it to do something. So you have multiple levels of communication that your algorithm and your code has to deal with, intranode, intranode, and then the GPU itself has multiple hierarchies of memory. The GPU, because it's got so many processors, they don't share a flat memory space. That was always bottleneck. The reason why we don't have 100-core computer clusters is that people can't, these processors get into each other's way when they try to address the same memory. So GPUs say, well, we know that they're going to they have like 2,000 cores on one GPU, and those 2,000 cores, they don't try to compete with the same memory. They all have local memory that they have to talk to, and this global memory, local memory has some way of interacting with their onboard memory. So when you buy a GPU with a gig of RAM on board, this gig is on one hand shared between your 2,000 cores, but each the nomenclature is very strange. Each of these 2000 cores has local memory, which is called shared. It's not shared. It's actually the global memory is shared. The shared memory is not shared. Local to clusters of GPUs. So the problem now is that the memory available to every core is only about 2 kilobytes at the end of the day. And again, that if you compare this to a CPU, any CPU has at least these days 2 megabytes or often 8 megabytes of cache. And here now we're talking about 2 kilobytes. That's 1/1000th of the memory that a CPU is available. We know that even for a CPU, if you're not computing in cache, you're not getting any performance. So for GPUs, it's equally essential to keep your memory there, except you've got no memory. And again, the logic is very simple. If you ask, how many transistors do I need to do a multiply? You say, I don't know, it takes a few thousand. Then if you say, well, then if I have more than about 2 kilobytes of cache on my machine, all my transistors are going into the cache and almost nothing is going into my multiplying units. So the break-even point is somewhere around here, where about half your transistors are storing the data and half of them are computing on it. And so they push it about as far as you can. And that turns out this is about the break-even point, where the amount of memory balances the amount of compute power. And that's about 100 numbers. Which means everything you compute, you better fit in these numbers, and you better beat, just like in cache, you better have excellent memory reuse. You better, beat around these 100 numbers at least 1,000 times each before you write them back to the larger memory space. Otherwise, you're not getting performance. So this is the new algorithmic constraint: is to program with tiny caches that you have to explicitly specify. So when you declare a variable, you've got to say, I want it in cache or I don't want it in cache. So it's a very, it's I would say even a lower level than assembly. For anybody who's ever dealt with the pain of programming assembly, this is worse than assembly. This is one more headache than assembly language programming. And that's what you have to do to get any performance out of it. So the programming paradigm is now fairly complex. You need to have an MPI, a message passing interface, for the nodes to talk to each other. You need to program in C to just control all of this thing. Now the GPUs are programmed in the languages which support this hierarchy of memory. There are currently 2 main contenders: CUDA, developed by NVIDIA, and OpenCL, which is a vendor-independent one, that programs the GPUs themselves. And the GPUs themselves, well, within these languages, they have branches of vectorization and other issues. So it's a major pain to do anything. So it's not a good casual place to get started. So luckily, our ideal gas code is relatively straightforward. It's a 400-line code, which is short on the scale of codes for the single CPU version. By the way, GPUs, they do really well on the matrix multiplies. Okay, matrix multiply is a 4-line code. And for those, people have benchmarked GPUs and they perform amazingly well. And that's when they rewrite this matrix multiply, which is 4 lines in C or Fortran. It becomes like 1,000 lines of OpenCL code. And that's how you get the speed out. So the code base grows by a few orders of magnitude. A factor of 100, I think, is the kind of extra complexity. It's like compiling this into assembly, right? 400 lines in assembly is a lot of lines. So that's what you're talking about. But you're doing it by hand. So the scientist becomes the programmer. And we've been implementing this, and when I say it reduces pain, is that we've got a short code to start with. That's how you reduce the pain. It's still painful. So, and in fact, we've implemented, BJ has implemented this code on a variety of architectures, meaning right of GPUs, ranging from NVIDIA's, which are well known, ATI, probably everybody has heard of, the IBM Cell, which is based on the PlayStation 3 processors, so the IBM Toshiba processors. And if you ask, how long each of these things took, those take significant, substantial version to implement. But he got it to work, and we do seem to get some of these things to work. Our main bottleneck is, again, a little bit technical, but it turns out that we do get good speed up, except that we're actually limited not by the theoretical peak speed on the GPUs. And again, we're still doing much faster than CPU, but our current bottleneck is given by the streaming speed from the local cache, which is not that big, 2 kilobytes. There's only so much work I can do before I have to write the data back. And the internal bus speed, even though the GPUs do use very high-speed memory, they tend to have DDR5 and very expensive stuff on there. But even there, that becomes our bottleneck. And that kind of limits how fast it actually runs. I think the rest is a little bit more technical than I need to go into. Here's a basic summary of how fast performance we've been able to gain. So how long a code takes to run on one processor, on one CPU. That's I didn't write it, but it's like a 2.5 gigahertz Nehalem processor that this was benchmarked on. Unfortunately, this is too generic a label. That doesn't mean anything at all. This could have been a 30-year-old processor for all this tells you. It's actually the latest of its time. I think one comparison, of course, on NVIDIA, as I said, the speed up, it runs in 64 seconds. So it actually runs 137 times faster on a Tesla C2060, which is the same as the GTX 280 if you want to buy a gaming version of it. So yeah, it's a good speed up, a factor of 137 times faster. Comparison is a little bit unfair because nowadays, of course, nobody would run a code on a single core. Running it on 8 cores is just a matter of adding a few directives, which takes no effort at all, and you actually get a factor of almost 7 speed up. So it's really more these two that you would ever really want to compare. Nobody would ever run on one core anyway. So, but still a factor of 20 is a kind of realistic speed up, and of course, an 8-core machine costs a similar amount as a GPU box, so again, depending on the right here. So, yes, we do get the kind of speed ups that scaling that's promised, but it just takes a lot of work to code. And the MPI, it turns out we have got a very slow network. So again, I'm not going to go, this number is a little bit too technical, but we do get speed up of a factor of now against the CPU, against the full thing, of only a factor of between 2.5 and 1.5 relative to the CPU, because when you run on GPUs, all of a sudden our network becomes our bottleneck of communicating between nodes. So if you want to have the old code running on a slow network, we don't actually get to materialize we get materialize some of it, but not nearly the factor of 20 that we had before. You get a factor of 2 after you're through this network. So this requires, there are ways around that. The ways around that is to either buy a faster network, and of course we're running on regular gigabit Ethernet. You can go to InfiniBand, that's a factor of 40 faster. So we can pay money and make this go faster. Or you could try to come up with algorithms that just communicate less intrinsically. So again, you are pushed into new ways of thinking about the problem. Right now, this test is really running the exact same algorithm, having to give you the exact same answer to all significant digits. And that's the speed up we get. And often what happens is as the architecture changes, you just change the way you actually implement it. The same algorithm just may not be the one that you actually want to use in this kind of setup. That summary is that, yeah, these GPUs work. You got to be careful. It's a lot of work, a lot of details. Let's not worry about that. And let me just summarize of our experience that we think we have a new paradigm for this general category of the galactic centers called non-radiative black holes. Non-radiative just saying that they don't radiate, like they're not as bright as you'd expect them to be. And we call these things magnetically frustrated flows. And we hope to be able to test this paradigm in the next upcoming years to see whether this picture is really what's going on. That this new category of doing systematic global numerical experiments has really only been possible with modern HPC infrastructures of running on tens of thousands of cores. Our paradigm is nowadays what's already called classical message passing. Again, 20 years ago, this word didn't even exist. So this is already a new step that everybody had to adopt to make any use of computers. And I think the future may be in yet one more level of specialization of algorithms to make use of the next generation of infrastructure. Good, no rest of the details. Thank you.
Thanks. I have a question.
Of course.
So I went to a talk by there's a fellow named D.E. Shaw, who was, I guess, started his own hedge fund in Wall Street, so he became very wealthy, and then decided he wanted to get into biological research. One of the problems that fascinated him was simulating protein folding. So what happens when you have a sequence of this protein, and then you unravel the thing, let it go, and see how it folds back on itself, and all these different levels of structure that he wanted to predict, and so on and so forth. And his approach, so he was also using high-performance computing to try to, people try machine learning approaches where they try to statistically predict the likelihood of these structures forming given from low to high level. But his approach is actually just brute force simulation in these, what I would call it was these essentially very specialized processors where he essentially encoded the laws of physics, and then he made lots and lots of processors, and then just kind of set the thing off and went. So I'm just curious to know your, does that kind of approach make any sense for, he seemed to think it made sense for biology, and he actually showed some pretty impressive simulations where he was able to simulate the first in a microsecond or something, and folding pretty rapidly. I was just curious about how, the trade-off between creating these custom processors with a very specific knowledge of, particular laws at a very small scale versus this generalized GPU type of processors. I mean, there are obvious benefits to using the more general machines. You make a mistake, and how you choose or implement the laws of physics and these things, it's a lot of work to redo. And on the other hand, he supposedly thought that that cost was worth the benefit of the extreme performance here.
Yeah, I mean, there have been various applications, including proteins, of building custom hardware that kind of has the problem you have hardwired. Some other applications that I've heard of include, for example, lattice quantum chromodynamics. People have built custom computers. In the past, people have built chess computers to play chess. It's depending on the problem, people have built specialized computers, and some of them have had success. I think in the long run, obviously, at a given stage, sometimes these are more economical than because now you're not wasting all these. Even with GPUs, you're still wasting most of your codes doing operations that your problem might not need. So obviously you can maybe get another factor of 10 gain in how much you can squeeze out of the same number of transistors if you know what your problem has. But as you say, the trade-off is, there are two types of trade-off. One is flexibility, what if you got it wrong? But in history, so, some of these problems are very clean, like chess, the rules of chess. As long as the Chess Federation doesn't change those rules, which they don't do very often, your computer is probably good to go for a while. So those are very simple rules. And yet, what they've had a hard time keeping up with is Moore's law. These general purpose things, fine. This you think that you've worked 10 years on to make fast, maybe the fastest thing out there. But the problem is 3 years downstream, well, the general purpose ones, again, have overtaken. You've got to start from scratch, designing something new for the next, hardware technology. So it is this thing that the specialized computers have had a hard time keeping up with mass production. And as long as Moore's law keeps going, I think we will only see niches popping up once in a while. If Moore's law ever saturates, which it's got to do someday, once Moore's law saturates, then I think you will see much more of that, because the only way to make things faster is to specialize, and people will be building. That'll be probably the only game in town. Will be for every problem we'll build our own machine, and someday we'll probably get there. One piece of amusing trivia is that Moore's law has been going on for about 50 years roughly. It's about 50 years ago that 40 years ago that he observed it, but he'd been observing it for a number of years. It's been doubling in speed every 18 months, or doubling in transistor count really. That's what it's been doubling. The speed hasn't gone up anyway. But it's been doubling in complexity every 18 months for the last 50 years. And you can easily show that if you did it for another 50 years, then 50 years from now, which may well be in our lifetime, you would have to make one computation with every electron in the Earth on every orbit around its atom. Okay? And that seems pretty ambitious. So it seems unlikely that Moore's law will last another 50 years. So it's going to bottom out, and yes, then the story will change.
Thanks very much.